Today's talk, it's going to be a good one, covering a lot of different topics from Bryce Hesterman here from Utah State University. And is going to talk lots of good stuff about modeling transformer and some of the effects, and as well as the real measured data from that. I would like to mention that Bryce has generously not only given his permission for us to record this so we can make it available to you for post afterward, which is on our website, which we'll show in a minute, but he's also made available to share his slides, a PDF of his slides. So that information will be distributed to all registered attendees through the Eventbrite thing after the event. So please do not put in the chat or the Q&A asking about if you're going to get the slides or when or whatever. That will all come afterwards. But what we do want you to put in the window, especially the Q&A window, if you have any questions for our speaker, please be sure to put it in the Q&A window. Again, not the chat, but the Q&A window. And we'll mostly save all those to the end, and then we will address those with our speaker. We want to thank very much our main co-sponsor for today's event, the Santa Clara Valley Magnetic Society. Apologies, guys, I couldn't find a better resolution image, but there's a link to their website and all that, so you can find out all about them. And additionally, we have today's kind of a special event in that we have many other PELS chapters helping to spread the word about this. So we've really spread the reach, actually internationally. Yeah, I just want to just recognize the ones at least I'm aware of specifically. So welcome to PELS Seattle chapter, which is the former one chaired by our speaker today, Bryce. PELS Utah student chapter, our speaker is now current chapter, as well as PELS Pittsburgh, PELS Charlotte area, PELS Baltimore, PELS Boston, and Long Island. And of course, also at the society level, the office and everything always gives us fantastic support. So thank you very much to all of you for helping to publicize today's event, and welcome to all the members of all those various orgs, if that's how you found your way here today. Want to recognize the XCOM here, the executive committee for the Bay Area PELS here, that they're the ones who make all this happen. So there they are listed, and thank you to them as always for keeping us alive and helping us bring these great events to you guys. That is it. So yeah, thanks very much again on behalf of the XCOM and our sponsors. And with no further ado, let me stop sharing, and I would like to turn it over to our distinguished speaker today, Bryce. Bryce, why don't you go ahead and pull up your slides, and I will, as I prepare to introduce you. Okay, Bryce Hesterman, he's a principal research engineer at the Utah State University Power Electronics Laboratory, where he provides advanced engineering support, oversight, and leadership on major research and development projects related to electric transportation. Bryce received his BSEE and MSEE degrees from Brigham Young University. He's been awarded 24 patents and has a wide range of experience in power electronics design and analysis. He's an active member of IEEE and formerly served as the chair of the Seattle chapter of the IEEE Power Electronics Society. So with that, thank you very much, sir, and the floor is yours.
Okay, thanks, Brian. So, this presentation introduces a circuit simulation model that includes both inductive coupling and mutual resistance effects. I'll start by reviewing the concepts of mutual inductance and mutual resistance. Because coupling and loss effects are largely determined by what happens outside of the core, this model works well even with nonlinear cores in cases where saturation is avoided. The model parameters are extracted in the frequency domain, but the models also work well in the time domain. And this modeling approach is particularly suited for cases not covered by Dowell's method, such as some integrated magnetics and transformers with multiple output windings. A transformer for a phase-shifted bridge converter is used as an example to illustrate the modeling approach today. Okay, so some limitations on Dowell's method. First, the method is used to calculate the AC resistance of transformer winding, but it assumes an infinite magnetizing inductance, which means that there's equal and opposite amp turns. But it's not intended for low permeability or gapped cores, and it assumes there's one independent current variable. In other words, all the currents are scaled by turns ratios. You can interleave the windings if they're connected in series, but multiple outputs with independent load currents are not supported by that technique. And windings in parallel are not supported because the current sharing ratio is unknown. Okay, short review of magnetic coupling. We've got two windings are coupled when some of the magnetic flux produced by currents flowing in either of the windings passes through both windings, and only part of the flux produced by one winding reaches the other windings. Usually it's quite a bit, but if you have an integrated magnetic, it may not be that much. And the flux which doesn't pass through both windings is called leakage flux. And the magnetic coupling can also be modeled in terms of self and mutual impedances. So here are the basic equations for two windings. We've got a voltage on either side. Notice that the current arrows both point towards the dot, and basically the voltage is equal to the mutual impedance of one winding times its current, times the impedance of one winding times its current, plus the mutual impedance times the current in the other winding. Now, we can extend this out to as many windings as you need, and this equation here is for a frequency domain model of the voltages and windings currents, and the values of the impedance matrix can be obtained through finite element simulations or extracted from measurements. Now, the thing that makes this difficult for time domain is that the impedance matrix values vary with frequency. And I'll be showing a method today that accommodates that. And it's important to note that the impedance matrices are symmetric. Okay, so this is the result of a finite element simulation in ANSYS Maxwell. And what it does is produces the resistance and inductance values at all of the frequencies that you simulate. And I've developed a MathCAD file that can parse this and then process it. I won't be going into the details of how that's done, but I did do a presentation on this at the recent PSMA Magnetics seminar in June, and eventually that presentation will be opened up to everyone, not the attendees. And if you're interested in learning more about what my methodology is, I'll be glad to share that with anyone who's interested. Okay, so I wound two transformers for my phase-shifted bridge converter. The first one had 3 layers of 2 Nomex between the windings. And when I connected it up, it looked like I was getting some noise issues. It turns out that wasn't really what was going on. It was a miswiring. But I thought, okay, I'm going to wind myself another transformer and put in more distance and get those capacitances down. And it turned out to be a fortunate thing because it allowed me to do some comparisons that I hadn't originally thought of doing. But I did end up leaving the transformer with the greater spacing between windings in, and I did all the measurements with that. Okay, so here's a simulation of finite element analysis, and I'm showing it modeled with 3 layers and 10 layers. And as expected, the inductances are pretty constant. And there's no capacitance involved in the finite element simulation. If you need to do a simulation with capacitance, you'd have to use something like HFSS instead of Maxwell. Okay, self-resistances. Here we're seeing the resistance of each winding varying with frequency, and the plots are pretty similar regardless of the spacing. Okay, mutual inductances, and again, the mutual inductances are pretty equal, but they're not exactly between the two, but you won't see it unless you really looked in at the fine details. What really shows the differences is when we look at the leakage inductances. Okay, mutual resistances between the 2 windings, or the 2 transformers. And what you'll see is that for the one with the 3 layers, what we're seeing is a pretty strong negative mutual resistance. And I'm going to show what the example, or I'm going to show the effect of this later on. But first, let's look at the definition of leakage impedance. So the leakage impedance is the impedance measured at one winding when another winding is shorted. And in the case of Maxwell, what you do is you take the impedances that it produces, and then you plug them into this equation, and it computes what the leakage impedance would be. And one of the consequences of the leakage impedance and how it's defined is that it's defined for a pair of windings. I know it's common when we're modeling a 2-winding transformer to split up leakage between primary and secondary, but in general you can't do that. In general, you can't put a discrete leakage inductance on each winding once you get more than 2. There's some special cases where you can, but in general, that doesn't work. And so you have to go about this another way if you really want to get a good model of the transformer. Okay, here are the leakage inductances. And what you'll see is the one with the more layers of Nomex has higher leakage inductance. That's just what you'd expect. The shapes of the curves are somewhat similar, but a little bit different. Okay, leakage resistances. So here we're seeing that they're pretty much the same. The leakage resistances don't depend on the spacing between the windings as the leakage inductances do. Now, we can define an inductive coupling coefficient to measure the coupling between the windings. And you'll see that with the increased spacing between the windings, that the couplings go down. Now, there's once you get more than 2 windings, you have to have some additional restrictions. And there's a reference 9 that I give, and it explains what it is. But basically, you have to have what's called a positive definite matrix. And if you don't have a positive definite matrix, and then you create the system equations, what you'll get is e to the positive t instead of e to the minus t. And so your part is no longer passive, becomes an energy source, which makes no sense. So you really do have to watch. those couplings. And fortunately, LT Spice has an automatic check. If you put in something that's going to make the simulation blow up, it lets you know. Sabre does that as well. I'm not aware of any other circuit simulators that do that, so you need to make sure that you have an appropriate set of couplings when you do your simulation. Okay, now here's something most of you probably have not seen. You can define a resistive coupling coefficient matrix. And the values of each coupling are defined with an equation that has the same form as the magnetic coupling. And the coupling coefficient is negative when the mutual resistance is negative. I haven't seen this used in terms of transformers, but where I have seen it published is for induction heating, where they're very much concerned about what the resistance is of the load or target, so they define this, and I found that the same thing is quite useful for transformers, as I'm going to show. But what you will notice is we've got this really significant negative resistance coupling for the first transformer, and a little bit for the second one. All right. So here we have a situation where I'm measuring leakage resistance, and I've got two windings, 2 and 3, and the sum of the primary, say not primary, but we'll call it the second winding and the third winding, is greater than the sum of the leakage resistance, and that's because of the mutual resistance. It works pretty much the same way as for magnetic coupling, in that if you measure the inductance on one winding and you short another winding, the inductance that you measure goes down. Same thing happens with resistance. It's just that the coupling coefficients for magnetics tend to be fairly constant, but for resistance, they can vary all over the place. Okay, so this is for the second transformer, and in this case, the mutual resistance coupling is higher. The other one was 0.8, this is 0.9, and consequently, the cancellation, or the decrease in reductance, decrease in resistance, is actually greater. Okay, now we're going to look at the one with the strong negative mutual resistance coupling. And what you'll see right at the point here where it flips sign, the order of the windings flips also. This means that when you short the second winding, the resistance goes up. And this is something that I had never seen before until I started simulating and measuring these things. The thing that seems to make this happen is when you have windings that aren't adjacent, and you're getting losses of the windings in between those two windings. This is an area of ongoing research for me, and I hope to eventually publish something on this that really looks into this mutual resistance and why it's positive sometimes and negative other times. Okay, so the second transformer, you'll see that this mutual resistance coupling is much less. It's a little bit negative, but not so far as the other one, which was down here. And now these two curves, they just kind of line up on top of each other instead of having this one pop up over the other one. I decided that I would take a look at the resistance of one winding as I was building a transformer, and then see how it would change when I added the other winding. And so this is the impedance of the isolated winding. It's self-resistant and inductive. And then I finished the transformer and finished the model And this is what I have of the 12 turns, 4 turns, and oh boy, I see a typo. That's supposed to be 4 also. So it's 12, 4, 4, and 12, all of which is with 1-inch copper foil, and the inner 2 windings have thicker foil than the other. All right, so this is comparing the transformer winding by itself, and then the same winding inside of a transformer. And again, this is the finite element simulation, but what it's showing is that the resistance is higher when I start adding the other winding. This is an equivalent circuit that I came up with, and it's different than a typical equivalent circuit for, say, one winding or an inductor. Typically what you do is you put several inductors in series and you vary the value of the inductors and the value of a resistor. And when you're all done, you can match the Dowell's curve pretty well. I took a different approach. In this case, I've got auxiliary inductors. These inductors are coupled to this winding, and I made all of the inductances of the auxiliaries equal to this inductor up here. That was arbitrary, but it's convenient for the math. And then I vary the value of the parallel resistor and the value of the coupling back to this winding. And I don't couple these windings to each other. Now, you can't build something like that, but mathematically, you can do it, you can simulate it, and it's useful. You can think about it as like within one winding, there's eddy effects going on, and those effects kind of are in that winding. And then anyway, you'll see here in a bit what happens when I put everything together. So here's a winding by itself, same winding within a transformer, and I've got an equivalent circuit for both that matches the simulated data pretty well. So here's the equivalent circuit for the 4-winding transformer. I've got the 4 windings that represent the physical windings, and I put in 3 auxiliaries for each of the physical windings. You don't have to have 3. You could use 1, 2. I found that with 3, I could get really good matching all the way up to 10 megahertz. And it just gives your model more degrees of freedom if you add in some more auxiliaries. And again, I made all of the windings in a row equal to each other. Didn't have to do that, but it makes the analysis easier if you do it that way. And one thing I wanted to mention is that this concept was not developed by me. I read about it in a paper published in 2000. And I had some questions about it, and it was in one of those journals that allows authors to make comments or ask questions. So I did that. And one of the things I was asking about is, well, their model was had a full coupling matrix. In other words, like this winding here was coupled to every other winding, and this one was coupled to every other winding. And I said, well, I'm going to try simplifying it and just model these being coupled to each of the windings, but not to themselves and not to any of the other ones. And that simpler model turned out to work pretty well. And so that's what I've been doing ever since. So I've been doing this, using this type of modeling now for a little over 20 years. All right, here's the equivalent circuit as implemented in SPICE. So I've got my main windings up here that I can stick in my circuit where I want. Then over in a corner, I just hide this little circuit here with the auxiliaries, and I use an include statement so I don't have to clutter up my schematic, but I went and included what was in that include file here. And it looks like, oh man, that's a lot of stuff. But the MathCAD just generates all that and spits out a text file, and you don't have to type in anything. Okay, so here's a closer look of the modeling coefficients as they're implemented in MathCAD. You can see the physical windings have their couplings up here. The auxiliaries are out here, and then the rest are zeros. And it just makes the math a lot easier to deal with. And one of the things I do to check that I have an approach, whoops, beginning, I have a 3D mouse, and I accidentally bumped into that and started moving my slides. Sorry about that. I need to get back to where I was. Okay, here we go. Yeah, so what I do is I check the eigenvalues of this matrix, and as long as none of them are negative, then we're good to go. All right, now, one of the problems when you get to a real transformer winding is it's got capacitance, and that creates resonances, and then that obscures your ability to figure out what's really going on with the resistances. And so what I did is I came up with a method that I start out with a series inductance and resistance, and then by doing some parallel and series manipulations, I essentially subtract out the effect of the capacitance. And it works pretty well for the inductance. And the resistance, it doesn't work quite as well at canceling, but what it does is it enables me to get way closer to resonance in making measurements than I otherwise could. Okay, so now here's my finite element and equivalent circuit, self-resistances and inductances, and the equivalent circuit modeling of that. You can see the model is just laying right on top of the finite element results for the resistance. For the inductance, it's really pretty close too, but I zoomed in because the changes are so small as you go up in frequency that when I zoom it up, you can see these small differences here. While this is such big numbers that you can't really see these fine details. Okay, so this is for the measurement, and you'll see that I'm only measuring up to around 600 kilohertz. Things start to diverge above that, and it was just the best that I could do. I was using an HP 4194A network analyzer to do my measurements. And I did use the capacitance correction. This would have been quite a bit off, more off than it is here without that correction. Okay, here's the leakage inductances. And as you'd expect, the leakage inductances decrease with frequency. And I'll talk more about the consequences of that. What also I did is I plotted the Q of the leakage inductance. And the Q is, relatively low. If you have a transformer that's designed to have a resonating leakage inductance, you can get this Q up to 200 or more. But for an ordinary transformer, Qs of on the range of say 5 to 20 are pretty typical. Okay, this is doing the same thing but with measurements. And my equivalent circuit model is not perfect, but it's still reasonably good. And the match is a little worse on the lower values than it is, say, on the higher values. Okay, the leakage resistances, and again, the match is pretty good. And this is for the measured, and you can see that for both of them, they're pretty good matches. And then we have here the equivalent circuit mutual resistances. And then for the measured one, and for the measured ones, I can't go up as high in frequency before the capacitive effects become as great. Okay, now here's the resistance coupling. And we've got a really good match on that for the finite element. And for the measured, the match isn't as good. But it's still, it's pretty good up to a megahertz or more. And notice the shape is a little different. And one of the things that happens when you build a real transformer is that the core actually participates somewhat in the mutual resistances, and it didn't in the finite element because I set the core loss as equal to 0, so I could just look at the copper loss. Okay, so here's a SPICE simulation. I want to measure the impedance, the self-impedance, and so I just put a 1 amp current into one winding. I leave the others open. There's my auxiliaries, and that's what I get. And this matches the MathCAD, and so I know that the SPICE model is tracking the equations that I used to generate the model with. And then leakage, and I go here and I short a winding, and then measure the voltage here with the same 1 amp. And now I can see I have my leakage resistance and the leakage resistance with, say, winding. Well, this is with, it's the same thing, but with more insulation. But what I noticed was that what you really got was a shift in the leakage inductance. The drop here in this curve and over here is almost identical. The resistances are almost identical, but this is shifted up because of the extra energy stored in the field in the area where there's insulation. This is a picture of what I built. I had a TI demo board, and then I pulled out their transformer, put in my own ZVS inductor, built my own transformer, and you can see my resistive load there in the background. So this is my power stage of my phase shifted bridge converter. I didn't put any snubbers in. Instead, I put in some clamp diodes, and that prevents the voltages here from getting out of line, because let's say if this voltage becomes too great, this one down here will clamp it. Okay, so here's some simulations, and I took a lot of data under different conditions and checked to see how did the measurement do in comparison to the SPICE for my 2 output windings. And here we have the load resistances both equal to essentially 6 ohms. And then I have one at 6 and one at 106. I just added a 100 ohm resistor in series, and then both of them here at 106. To me, the most interesting result is when I took the resistance on the positive output, which is where I got my feedback from, and then kept the 6 ohms on the other load. And what I found is, yeah, it kept on regulating the output of the measured one, but the other one dropped all the way down to 2 volts. And what was really going on is that the pulse width became quite narrow, and with the narrow pulse width, I could maintain my output, my regulated voltage, but the other load, just dropped out. And so this is something that actually does happen in converters. You have to be careful about your loading, and if you're just regulating off of one and off of one winding, then things can go really wrong on another one if your main winding becomes, very lightly loaded. And so I did this for SPICE based on the finite element data and on the measured data. And the results are really very close. You can see that the measured data produced a circuit model that was really quite good. Then I created a bigger ZVS inductor and then compared that, and again, things are tracking really well. Okay, so now let's look at some winding or some waveforms. And now the waveforms aren't perfect. They were producing the right results in terms of DC voltages, but one of the things I wanted to really check was I've got a primary winding split, first layer, last layer, time and parallel. Sometimes people say that causes big circulating currents. I haven't seen that. What I have seen, though, is that the secondary, or the second winding, the outer layer winding, carries less current than the first one, but not a whole lot less. It's like 25%, 24% more current in this winding than this winding. On the other hand, the outer layer winding has more resistance. So it's actually convenient that the current is a little less. It kind of optimizes the losses automatically. And the other thing that making a connection like this does is it reduces the leakage inductances to have your primary split. You can also put the primary windings in series, but I found that there's some advantages to putting it in parallel, so that's what I did here. And again, finite element, SPICE, I'm getting pretty reasonable correspondence. And then this is the measurement-based SPICE. Again, it's tracking the RMS current values quite nicely. And then this is with the bigger ZVS inductance. And again, it's tracking pretty well. And for both the finite element and the measure. Okay, so now let's look at the situation with the actual, more of the waveform shown. And one of the things I did is I used SPICE to calculate all the losses in the auxiliary resistors, which represent the high frequency losses. And then in the resistors that represent the DCR, then I looked at those losses. And if you compare what goes on with a 10.7 microhenry ZVS compared to 2.4, is you'll see that adding more ZVS inductance decreases the high frequency losses pretty considerably, but the low frequency losses remain about the same. And so if you have a problem with high frequency losses in a phase shifted bridge transformer, increasing the ZVS inductance can really bring your losses down. In a case of some transformers I designed for NASA, I was able to cut the transformer losses in half by increasing the ZVS inductance and the losses in the ZVS inductance itself were small enough that the overall losses went down quite a bit, and the project was able to meet its efficiency targets, which it previously didn't. Okay, so this is doing it from the SPICE model based on the SPICE measurements, and you'll see, the SPICE based on the measured data as opposed to finite element, and you're seeing some bigger losses here, but that's partly because the auxiliary resistances are now picking up some of the core losses in the way the model was done. Okay, now, this is from a different transformer, but I wanted to share the results of a test that I did. Same core, same number of windings, but they're wire instead of foil. What I wanted to do was to look at the decrease in leakage inductance with frequency and show some effects of that on the circuit. This is like a real, this is a model, basically my same model method with my windings in parallel, and then I shorted the two secondary windings. And we know that the voltage is equal to the inductance times the derivative of the current. Well, you can turn that around and say, if I know the voltage and the derivative of the current, I can compute the inductance. And so what I did is I went in and performed that simulation and used the derivative function in LT SPICE. And what you'll see is as the pulse width increases, the apparent leakage inductance goes up. But if you're interested in diode reverse recovery, well, that's going to happen down in here. And so what that says is, if you want to know how your circuit is going to perform and you've just got fixed inductances and you don't have a variable frequency model, you want to use the lower value of leakage inductances measured at high frequencies, because that is what will give you the best results, most realistic. And here's a diode reverse recovery test circuit. I've actually built one of these. I don't have one. I left it at my last employer, but I intend to build another one. Anyway, with that test circuit, you can look at the effects of the diode reverse recovery. And when I used the mutual inductance, and that part isn't shown in this slide, but it's either there or not there in the SPICE, you can see with the mutual resistance enabled that you get a quite a bit different reverse current than with the mutual resistance modeling disabled, which means the leakage inductance was higher, which would not be as realistic. So my conclusions here, you can make the mutual resistance circuit model match the finite element results pretty closely, and it matches the measured data pretty well, but you have to compensate for the capacitance to make it more accurate. And the SPICE circuit models produced by the finite element simulations are more accurate at predicting the current sharing than the models produced by LCR measurements, but they're still pretty good, both of them. And then the DC model results for both the measurement model and the finite element based model, they both predicted the DC really well. And all of the model variations were able to capture this loading issue where one winding dropped to 2 volts. And then more conclusions: the leakage inductance for closely coupled winding pairs decreases with frequency because of the skin and proximity effects. And you can look at the effective leakage inductance for pulse waveforms by looking at the basically dividing the applied voltage by the time derivative of the current. And the leakage inductance for short pulses is less than for longer pulses. And so that affects the reverse recovery. And I've got some example files on my personal website at this link. And so this concludes my presentation.
All right. Well, thank you very much, Bryce. And also a very excellent sticking to the time frame for a lot of great content. So kudos to you for that. Hey, while I remind people what they can do now, why don't you start making your way over to slide 24, because that will involve our first question. Our first question comes to us from an anonymous attendee. And he says that if I remember correctly, on slide 24, you said you are using 1-inch copper foil. Because if this copper foil is used for the windings, how do you get the foil closest to the core out to make a connection to it?
Okay. So the way I did that is I soldered wire onto the foil. And in this case, what I did is I took some, I believe it was 20 gauge wire, and I flattened it and then soldered it on and then brought that out the side. I have used flatlets wire to make connections when I wanted to do a really high efficiency transformer. And that Litz wire is a little hard to get, but that's what I did for my NASA transformers. Was I used flat Litz wire on to make the terminations.
All right.
Next.
Well, I'm a man after my own blue wire heart. Next question comes to us from Alireza Safi. And he says, maybe I missed the equations to calculate the extra resistances. Can we see them again, please?
Oops. All right. So this is like the definition equation. And as far as what produced it in the slides, that was based on either extracting it from the finite element model or from the equivalent circuit model. So there are equations for this that you can use for the equivalent circuit model. They're matrix equations. They're kind of hairy. And how would I put it? Well, when we discussed doing this presentation, we decided I would leave out the more complicated math. But it's on my website if you want to see it. You go to that link and you can see the entire MathCAD. I've got it in both MathCAD and PDF format for my PSMA presentation. And eventually I'll get stuff for this presentation on my website as well. So you can actually go through and see how I did it.
All right, thank you. Let's see, the next question comes to us from Gary Embler. And Gary asks, and I apologize if I'm screwing up the pronunciation here, but he says Butenbach permeance capacitance analogies versus Hopkinson's reluctance resistance analogies. What's your view?
There's I looked at the capacitance model, and when I was looking at it, it was from a different author, and basically, if you can make them to be mathematically equivalent, both of them have their uses, and there's some circuit simulators that have the inductance resistance model, and some people do homebrew stuff, say in SPICE, where you don't have that built in. You can do it with the capacitance model, and make it work quite nicely. And you can even do nonlinear capacitances.
All
That's
right.
not the topic.
I'm sorry? Oh, I'm sorry. Sure, Bryce,
That's not the topic of this presentation, if I understood the question correctly.
All right. Well, fair enough. Hopefully, we've addressed it to Gary's satisfaction there. Go ahead. Feel free to enter a refining question if need be, Gary. So it's interesting. I know you mentioned here, Bryce, that the whole point of this is a simplified model that you can run in SPICE, so that you don't have to do a full wave type of simulation and all this. So I guess one thing is just to you've shown that especially compared to other methods, that this overlays well and all that. So maybe if you could just quickly comment on kind of the trade-off in, time and effort and computation time versus getting to results and the accuracy of all that. Just expand a little bit on that and the benefit of this.
Right. So I'll give you an example here. So I used to work for Aerojet Rocketdyne and did a lot of work for NASA, and it took forever to get our parts made, and they were really expensive, like $5,000 to wind one transformer. And so it was really worth my while to refine things in Maxwell, and I could use this MathCAD in conjunction with the Maxwell. So it would take maybe 20 minutes to run a sweep in Maxwell, and then I can very easily pop that in to MathCAD and then get a SPICE simulation and look at it. And of course, to build something, then you've got to build it, and then going in and using a network analyzer and getting all the data out of that and entering stuff in, that might take a couple hours to create a SPICE model using a network analyzer. So you can actually do it faster in simulation than from measurement, at least with the equipment I have. Now, to me, the ultimate goal is let's do this fast, okay? And using some analytical equations. Turns out it's hard to do that. But one company that is basically using artificial intelligence-based analysis is called Frenetic. I've done a little consulting for them. And it looks like it's going to be a pretty promising way to do things. There's also the PEMAG from ANSYS that allows you to graphically draw your transformer, and then it goes and sets up an ANSYS simulation and spits out some results in a model. And that's another way to do it. I think this model is a little more accurate than the PEMAG model and has a lot fewer components and runs faster.
All right. So like actually kind of related to that, Daniel Lottis, one of our co-sponsors, he's asking, so how steep would the learning curve be, for instance, for, a project like this and ANSYS Maxwell, is it closer to days or years?
All right. So, I mean, it takes some time to learn how to use Maxwell, no doubt about that. But one of the things I do to speed it up is they've got the PEMAG that comes with it. So I will graphically draw not a physical model, it's kind of a user interface where you wire up all the windings and then you run a simulation. And that whole process automates the Maxwell. And then what I've done is I've taken the model generated by PEMAG in Maxwell and then reused it for my own purposes and did my own frequency sweep and made my model from it. So it's definitely an investment in time. I felt strongly enough about this that back in 2013, I pulled out some retirement money and I bought myself a copy of Maxwell and showed what it could do. And eventually my employer got their own license. But I think it's, if you really want to get into the nitty gritties of understanding magnetics, finite element can do a lot for you.
All right. Hey, I think special mention here of all the, the efforts you mentioned to save your former employer money. By complete coincidence, my wife, who's sitting in the other room, happens to be a financial analyst for your former employer. So on her behalf, I'll let her know to make sure she really appreciates all that stuff you did to save them money. Hey, we'll take one final question, which is a good one here. But right before that, just a quick clarification. Someone had said, when you said you connected the, the foil windings outwardly, and you'd used a wire to couple that. They didn't hear the type of wire. They said it sounded like flat lids. What was the wire you used to connect the foil to the outer?
Okay, so basically I had some solid wire on hand, 20 gauge, and I basically flattened it to make it so that there wouldn't be as big of a bulge. You can buy flat wire, but
flat wire. Okay, that was, I think, the only thing. He just didn't hear that word. Yeah, that was it. It was flattened wire.
Flattened wire. But for my NASA transformers, I use flat Litz wire. In other words, it's Litz wire that's braided flat, and that is soldered onto the foil. And in those cases, we had lead wires coming out of a few inches. And so it turns out that I could actually save, like, I don't know, 5 to 10 watts in a big transformer by using flat Litz wire as the lead out instead of solid wire or stranded wire.
Sure. All right, thank you. And finally, we're just coming to the close here, but this is a good question, I think, for folks. It's a little general, but I think you can bring it into this context. And they're saying, an anonymous person has asked, what power conversion applications use transformers with foil windings?
Well, so typically high current. And these days, there's a lot more being done with planar transformers. But foil windings have been used for a long time to get high currents, and you get really good winding utilization that way. In other words, the copper that goes into your winding area, there's more of it than, say, with round wire. So that's where I've seen it used. And
all right.
And I want it here.
All right. Well, thank you very much again, Bryce, for an excellent presentation today and your time. And again, just one last time, I'd like to remind everyone, Bryce he agreed to make his materials available. So probably within 1 week of this event, we'll send a message out to all the Eventbrite registered attendees, and we'll provide information on how you can get access to the recording as well as a PDF of the materials today. And so with that, oh, I'm sorry, Bryce.
I was just going to say, if anybody wants to email me, my email address is on the first slide. I'd be glad to discuss it with anyone.
Okay, great. Yeah, actually, there was one question we didn't get to, and that's exactly what I told that person. So with that, and on behalf of Bryce, the Santa Clara Valley Bay Area Pels chapter, our co-sponsor, the Santa Clara Valley Magnetic Society, and the multiple other Pels chapters that supported this. Thank you very much for supporting this today, and particularly to all the attendees. Thanks very much for all you guys. Then we'd just be talking to ourselves. So thanks very much again. And that's going to conclude today's webinar, and hope you all have a great day and a great afternoon, a great evening, and remember to stay safe and healthy out there, and take care of each other. All right, thanks. Bye-bye.
All right.